Welcome to all in the next lecture of the determinant, that is on properties of the determinant. So here we will discuss about the properties of the determinant. So now here we have the first property is that the value of a determinant remains unchanged if its rows and columns are interchanged. So here, suppose we have this determinant. So here we have the rows are A1, B1, C1, A2, B2, C2, A3, B3, C3, right? So here we say that if we interchanged our rows or columns. So here if our rows was A1, B1, C1, now we interchange it by column A1, B1, C1, A2, B2, C2, A3, B3, C3. So now in this case the determinant has the same value. Means the determinant of A is equivalent to determinant of its transpose. Second is that if any rows or columns of a determinant are interchanged, then the value of the determinant is changed by the minus sign. So here suppose we have the determinant is this. So we are the elements A1, B1, C1, A2, B2, C2, A3, B3, C3. So now here if we apply that R2 is interchange R1, if we our R2 is this, if our R2 we interchange our R2 with R1, so in this case we have the determinant is with minus sign, means change in minus. Our R2 is convert into the R1 and R2 are interchanged, so the we have the minus sign of this value of the determinant, right? So according to that, like you can interchange any rows to other rows, but we have the minus sign with that. Next, third property is that if all the elements of a row or column is multiplied by a non-zero number k, then the value of the new determinant is k times the value of the determinant. Like that, if suppose our determinant is like that, here we can see that in our row 1 we have a scalar quantity multiplied k, ka1, kb1, kc1. So this determinant value is equivalent to the, if we take the k is common from this determinant a1, b1, c1, a2, b2, c2, a3, b3, c3. So in the determinant, if any number is multiplied, any row, all columns of row, or any all columns of or all elements of column, so we can take the outside of that, means the determinant of this value is equivalent to the k times of determinant of this value, right? And which also implies that if suppose we have this determinant a1, b1, c1, a2, b2, c2, a3, b3, c3, and we need to multiply any scalar quantity with any row or any column, so we have to divide is also there, means if we need to multiply ma1, mab1, mc1, so it is also we have to divide also this number 1 by m, ma1, mb1, mc1, right? Not only just you just multiplied this number but not divide that. Similarly number we have to multiply and divide. Next property is that if each element of any row or column consists of two or more terms, then the determinant can be expressed as the sum of two or more determinants. What is this? It is says that if suppose our determinant is like that a1 plus x, column c1 is a2 plus y and a3 plus z, and c2 is b1, b2, b3, c3 is c1, c2, c3. So now it's this determinant value is equivalent to the determinants of two determinants of sum, means a1, b1, c1. One time you can take the column c1 is a1, a2, a3, and plus in another determinant you can take the column c1 is x, y, z, and c2, c3 is same. So when you calculate this, when you verified this, and you can found that you will find that the determinant of this value is equivalent to the determinant of this. So we can say that if we have the any addition of two numbers in any row or in any column, so we can separate it by the two determinants. Next property is that the value of a determinant is unchanged if any row or column is multiplied by the by a number and then added to any other row or column. The value of a determinant is unchanged. So here we have this determinant a1 b1 c1 a2 b2 c2 a3 b3 c3, right? So now if suppose we apply this, so we apply this column value c1, so now c1 is interchanged into c1 plus mc2 minus nc3, right? So if we apply this operation, so now our changed in only the column c1, so now our column c1 becomes a1 plus mb1 minus nc1, a2 plus mb2 minus nc2, a3 plus mb3 minus nc3. So like that, if we do this operation, we use that c1 plus mc2 minus nc3. So now if we when you apply this operation, so now change is only in c1, right? So when which column we need to change, so we have to write that column in first place, c1. So now change is in only c1 column. So this determinant is equivalent to the this determinant, means according to the your proof, when you use your proof of the determinants, then you can use this. Okay, so in examples we can use this. Another method, another property is that if any two rows or columns of a determinant are identical, then its value is 0. So now suppose our determinant is that a1 b1 c1 a2 b2 c2 and r3 is a1 b1 c1. So our r1 and r3, here you can see that our r1 and r3 are same, right? So if any two rows or two columns are same, so its determinant value is 0. Next property is that if each element of a row or column of a determinant is 0, then its value is 0. Means suppose you have like that, here we see that our r1 element, all element of r1 is 0, right? So we can say that this determinant value is 0. Or if any column we have all elements are 0, so that determinant's value is 0. So you can say directly that this determinant value is 0. Now the next one property is that if you have suppose a matrix be a diagonal matrix. What is the diagonal matrix? You know what is the diagonal matrix? Actually diagonal matrix is that matrix in which we have the in diagonal we have the non-zero elements and non-diagonal elements all are the zero. So like that, this type of matrix is called the diagonal matrix. Then if we need to find the determinant of this, so what will be the determinant? The value of the determinant of the diagonal matrix, this is equal to ABC. ABC means we have to just multiply the non-diagonal elements. So that is the value of this determinant. Clear? Okay, so now we see here our row column operations, because when we need to verify our determinant or we find our the value of the determinant directly, so we use here the operations. So now what is that row and column operations? First is that we represent by ri. Ri means to denote the ith row. If any row we use, so we can name this r. Suppose we use first row, so r1, second row r2, third row r3. Clear? Next one is we can use the operation by interchange. Suppose we need to interchange rows, so we use ri. This is the sign of interchanged. Rj, r1 interchange, ri interchange to rj. Next operation we can use Ri implies Ri plus Krj. It means that we have to multiply by K in any row and the in any k in any row and with the corresponding element of ith row, or we add that. So this operation here, always you have to remember this, which rows we need to change, that is right in first place, right? So it means that when we use this operation, so it means that our ith row will be changed. So now we can use KRI to denote the multiplication of all element by ith row. So if we need to multiply in any row by any element, so we can represent it by KRI. Similarly, we all these notations we can used in our column operations, right? Like CI interchange to CI implies CI plus K CJ, right? With the column operations. Now, evaluation of determinant. Suppose if our determinants becomes 0 on putting x equal to alpha, then in that case x minus alpha is the factor of the determinant. See here, for an example, suppose we have this determinant delta. Here our determinant values are these: x square, x3, 5, 9, 16, 2, 4, 8. Then we can say, here we say that x equal to 2. How can we say that x equal to 2? So when we put, suppose here x equal to 2, then our determinant is 0. How is it 0? Because when we put here 2, so it become 2, 2 square 4, 2 cube 8. So here our first and third column become identical. And we know that the property, if any determinant we have the two rows or two columns are identical, then its determinant value is 0, right? So when we put here x equal to 2, so our determinant value is 0. So we can say that x minus 2 is a factor of this determinant. Clear? Next, now here we take some examples where we use these properties and find the value of the determinant directly. So here we have this determinant, and now find the value of this. You have the in earlier lecture we told you that we can find the value of the determinant, right, by the two methods, by the expansion, right? We can do the directly expansion of this in any row with any columns, or we can find the value of like that, I told you in earlier lecture. But if we can also find the value of this determinant by the using the property, and by using the property we can directly solve this, the value of this determinant. How is this? Like here, here we have the first column is 42, 28, 14, right? Second column is 173, third column is 642. So now we can write this 42, 6 multiply 7, 28 we can write this 4 multiply 7, and 14 we can write it 2 multiply by 7. So here we can say that one common element is there 7, which we can multiply it by c1. So now by using the property of kr1 we can take the common of 7 here. So now our determinant is 642, 173, 642, right? Now, after that, we can see here our C1 and C3. C1 and C3 are, what is that? C1 and C3 are identical, means same. So, what is that? Its determinant value is 0. So, because our C1 and C3 are identical, so its determinant value is 0. So, it means that the value of this determinant is 0. So, directly we can find the value of this determinant by using the property, because when you solve the this value by the expansion, then it is also becomes 0, but that will take the time. And for your, if you give any entrance or any other exam, so you need that you save your time and you use the property. So by using the property you can uh, easily find the value of the determinant. So now the second part, we have this. How can we use here our property? So we can write this 6 into minus 3 into minus 2. 2 we can write minus 1 into minus 2, because we need to one common element here. So minus 10 we can write this 5 into minus 2. So now we can take the common minus 2 from C1, right? So we can take the common minus 2. Now we have this. Now again we see that our C1 and C2 columns are identical. So this determinant value becomes 0. So we have the value of this given determinant is 0. Clear? Now, next we have to evaluate this determinant, means we need to find the value of this determinant. So now see, how can we solve this? By using the property. So when we do when we solve any determinant, so we can add the elements of the rows or we can add the elements of the column. So it's depend on you which property you want to use here by finding your result. So now what we do here, we use C3 plus C2, means we change in our C3. So we change in our C3, so we write C3 implies C3 plus C2, means we add in C3 our C2, so it become A plus B plus C, and it become A plus B plus C, it again become A plus B plus C, and C1 and C2 are same. So now change in C3. So which column or row we have the changed, so we write in the first place. So we write it C3 plus C2, not C2 plus C3. Okay, so we write here C3 plus C2. Now you see, which property we can use here. Here we see that A plus B plus C, or in our all C3 column we have A plus B plus C, so we can take common of this A plus B plus C from the C3. Now after that we see that our C1 and C3 columns are same, are identical, so it means that this determinant value is 0. So now this whole determinant value become the 0. Clear? Now let's take the another example. Here we have to show that the value of this determinant is equal to 0. So what we do here, how can we show this? So here you can see this is our first row B minus C, and the second column C minus A, and the second row, so the third row is A minus B. So suppose we add here in this R1 R2 R3, then what it becomes? C is cancel, minus A plus A is cancel, plus B minus B is cancel, right? So it becomes 0, right? So what we do here, we do R1 in our change in R1 only, right? R1, when we apply R1 plus R2 plus R3, it means our change in only R1, not in R2 and R3. R2 R3 will be same, only change in R1. So R1 is R1 plus R2 plus R3. So it become R1 is 0, because we use here R1 plus R2 plus R3. So all these, when we add this becomes 0. Similarly here, when we add this becomes 0. When we add these elements, this becomes 0, right? After that, we know that the property in which we have that if any row or any column all elements are 0, so that determinant value is 0, right? So we can prove this, that this determinate value is 0. Clear? Let's take another example here. Without expanding, actually it is also written here that without expanding show that this determinant is equal to 0 without expanding. So not directly we use the expansion of this. So we means that we need to use the property. So how can we use here the property? Actually here we have this BCCAAB, right? So now if we suppose multiply with A in our R1, and here we multiply with B in our R2, and multiply with C in R3, so it become ABC, it also become ABC, it also become ABC. We can assume this. So now what we do here, Here we multiply our first, second and third row by A, B, C. So when we multiply when we multiply an scalar quantity with any row, so we have to also divide that. So when we multiply A with R1, so we have to divide by A. When we multiplied with B in R2, so we have to also divide by B. When we multiply with C in R3, so we have to also divide C. So like that we divide this ABC and multiply it by, in R1 we use A, in R2 we use B, in R3 we multiply it with C, right? So now this determinant we have. After that, what we have here? Here we have that in this column C2, ABC, ABC, ABC are common. So we can take the common ABC from C2, right? So here we take the common ABC from C1, right? And C2 and C1 is also common, ABC, ABC, ABC. So from both the columns C1 and C2 we can take ABC. So now ABC from here and ABC from here, so it become ABC ka whole square, right? Now we when we solve this, so it become ABC, right? ABC, BCCA 111. Now after that, what we do here? Here we can add this and this, because when we add C3 in C1, so it become AB plus BC plus CA. Here again AB plus BC plus CA. Here it is again AB plus BC plus CA. So when we add C3 into C1, so we have make the same element. So now we can add this C3 in our change in our C3, that is C3 plus C1, right? So here we have make the same element. So now we can take common AB plus BC plus CA from the C3. So from C3 we can take common this AB plus BC plus CA. Now we can see that our C2 and C3 columns are identical. So its value, determinant value is 0. So now we can show that this determinant value is equivalent to 0. Clear? Now let's take another example. Here, without expanding, we have to show that this determinant is equivalent to this determinant and evaluate it. Evaluate it means we have to find the value is also of this determinant. First, we use this determinant and show that this is equivalent to this determinant. After that, we calculate the value of this determinant. So now first, we have this determinant. So what we do here? Here we need to a square b square c square. So what we do here, we can multiply with a of r1, multiply by b with r2 and multiply c by c with r3, right? So here we multiply first, second and third row by a b c. So when we multiply here, so it become a square abc, b square abc, c square abc, right? Now, so in last example like that, if we multiply ABC, so we have to also divide by ABC. Now next, we can take the common from the C3 column ABC, ABC, ABC. So now our element ABC is common from the column C3. Now we have this. Now, what we need? We need to prove that 111 ABC a square b square, and here we have ABC a square b square 111. So what we do here to interchange our this determinant into this determinant? So we need to interchange our columns, right? We need to interchange our columns. So first we interchange our C2 into C3, our C2 interchange in our C3. So C2 interchange in our C3. Now C3 is come here, a square b square c square. After that we need 1 here. So now we interchange our C1 to C2. So now we change our C1 into the C2. So now it become this. So first thing is prove that this determinant is equivalent to this determinant. Now further we need to find the value of this determinant. So see here, one most important thing, and you have to use this each and everywhere in the determinant when you find the when you expand the determinant. If you have suppose one row or any one column, that value is here 1 1 1, So like here our column C1 is 1 1 1. So we apply here always R2, change in R2 and R3. So R2 we change in the change in R2, that is R2 minus R1, and R3 change in R3 minus R1. But we why we do here this? Because when we apply R2 minus R1, so it becomes 0. When we multiply when we do operation here R3 minus R1, so it becomes 0. So whenever you have the one element in any row or in any column, so you have to apply this operation. So in our, if you have in column 1 1 1, so you need to apply the row operation, that is R2 minus R1, it becomes 0, R3 minus R1, it becomes 0, right? So we apply here this, and this operation not only in C1, that is operation all we use in our R2 and R3. So R1, because we change in our R2, so changes become in R2, and R3 will change, so R3 will change. So remaining same is R1. R1 will be same, 1 a square. And now R2 is R2 minus R1. So 1 minus 1 0, b minus a, and it is b square minus a square. Clear? Same R3 is changes by R3 minus R1. So it becomes 1 minus 1 0, c minus a, and it becomes c square minus a square. So like that you have to use your these operations. After that uh, you see that here you have in R2 b minus a, and what is the formula to expand b square minus a square? You know how to expand b square minus a square? So it become b minus a b plus a, and c square minus a square, we can write this c minus a c plus a. So now we can take common b minus a from R2 and C minus A from R3. So now we take this common B minus A, C minus A. So it become 1, 1, and this become B minus A and C minus A. Sorry, it becomes a B plus A, I think. So that is B minus A we take common. So it become B plus A and it becomes C plus A. Next, now what we do here we can expand our this determinate along the C1, because in C1 we have the two elements already has 0, so only we have to expand only one element. So it is easy that we expand our this determinant by the C1. So now expand along C1, and it become b minus a c minus a. So according to the b1, when we expand this, so it becomes c minus a minus b plus a. So now it become, we have b minus a c minus a c minus b, right? So now this determinate value is this, a minus b, b minus c, c minus a. Now let's take the another example. Here we have this, if x y z are different, if determinate this equal to 0, then we have to prove that xyz equal to minus 1, right? So now let's take this determinant xyz, x square y square z square. So now what we can do here we have the addition, one addition as element here, so in for our column C3, so we can separate it into the two determinants, right? Remember that property? So now our one determinant become x square 1, y square 1, z square 1, plus another determinant will become x square x cube, y square y cube, z square z cube. Now again we solve this, that what we do here, we can take x common from here R1, y take common from R2, and z take common from R3. So it become x y z common, so now it become 1 1 1 x y z, x square y square z square. And here what we do, we can interchange our C2 to C3. So when we interchange our C2 to C3, so minus sign will be there, right? After that, when we interchange this one, C1 to C2, so it become 1 1 1 xyz, and minus minus it become plus, right? And this is the same. Now you can see here this determinant and this determinant has the same. So now we can take the common of this determinant, so it become 1 plus xyz, and this determinant 1 1 1 xyz, x square y square z square. Now after that again we use our that thing here, because c1 is has the elements 1 1 1. So now we use here r2 is changed like r2 minus r1, and r3 is changed like r3 minus r1. So now 1 minus 1 it becomes 0, y minus x, and it is y square minus x square, y square minus x square. 1 minus 1 0, z minus x, and z square minus x square. Now here we have this 1 plus x y z. Now y minus x common here, z minus x common here, so it become y plus x, z plus x. Actually in the last example is also there, that is plus, not the minus there. Sorry, in the last example here that is like that, that will be plus here. Okay, so now 1 plus xyz. Now again we expand this by along our c1, so only we have to hide first row and the first column, so it becomes z plus x minus y minus x. So now according to that we have 1 plus xyz, x minus y minus z, z minus x. Now what we have in the question, actually in question is given that x y z all are different. So what it says that all are different means our x minus y not equal to 0, because all are different. If we say that x minus y equal to 0, it means x equal to y, but we have not this. In question it is already given that x y z has all the different. So our x minus y not equal to 0, y minus z is also not equal to 0, and z minus x not equal to 0. It means that 1 plus xyz equal to 0, because in question we have given that this determinant is equal to 0. So now from this we can say that xyz is equal to minus 1. We need to prove this. Clear how to prove this? Okay, so now let's take another example. Here we have this determinant 1 omega 3 omega 5 omega 3 1 omega 4 omega 5 omega 5 1 equal to 0, where omega is a cube root of unity. You know what is the property of cube root of unity? Actually in cube root of unity we have omega 3 omega cube, this is equal to 1 in the cube root of unity. It means that omega cube is equal to 1. So now we apply here this. Here we have this 1 omega omega 5. So what we can write this omega power 5? We can write this omega 3 into omega square. Similarly, this is omega 3, 1 omega 4. We can write this omega 3 into omega, and this omega 5. So we can write omega 3 into omega square, omega 5. So we can write 3 omega 3 omega square. Now, what we do here? We can take here, because this is the cube root of unity, and cube root of unity means omega cube equal to 1 we have. So put here omega cube equal to 1, so we have 1 1 omega square, 1 1 omega square omega 1. Now we can see here the determinant in our c1 and c2 are identical, are same. So it means that the value of this determinant is equal to 0, right? So now we have to prove this, that this determinant is equal to 0. Clear how to prove this? So like that you have to prove all the determinants values, and the given proof you can do by using your properties. Clear? So now thank you, today's lecture is completed. Now be happy, be healthy.